Hello everyone. Sorry I cannot speak Thai, so I'm going to speak in English. I'm going to deliver the presentation in English. I hope you're fine with that. So I'm Gabriel. I'm a senior solution architect at NVIDIA, covering APAC South, so Southeast Asia, Australia, New Zealand. So this area here. So I'm not too far from you. Whenever you need our help, we are only a flight away. And I'm going to talk about the different accelerated solutions that we have at NVIDIA for HPC, deep learning, and machine learning. I want to make this presentation interactive, so I have a lot of things to cover. We are doing a lot of things with KU, and we've been partnering with you for a long time. We know Professor Pujong, Professor Chantana for many years, and we are working on different projects. And I wanted to do an overview of the different solutions, different things that we announced recently. So we're going to cover a lot of things, but please feel free to stop me if you have any questions, or if you want to go deeper in one of the subjects. Okay. So this is the agenda for today. So we had Professor Pujong giving an introduction on the KU Center. We're going to talk about the different accelerated platform solutions at NVIDIA. We're going to talk about the convergence of HPC and AI. You've probably heard a lot about deep learning and HPC, but in different conversations. But more and more, these are actually becoming one single topic. We're going to talk about different deep learning SDKs, so you're going to see that NVIDIA is not just a hardware manufacturer. In fact, more than half of the employees at NVIDIA, half of the engineers, are actually working on software. So we're investing a lot of resources and a lot of work in making the software better and make sure that we get the maximum performance out of the GPU. We're going to have a short break. We're going to talk about something that we call NVIDIA GPU Cloud, and you're going to learn a little bit more what that is. We're also going to talk about the convergence of HPC and data science. Once again, data science was not necessarily something that we would talk in the context of HPC, but we did again work on the software side to release new libraries that allow you to tap into the traditional machine learning or run traditional machine learning on at scale. And we're going to have a use case from my colleague Eric Chung, who's going to talk about a similar implementation of both hardware and software. So we're going to talk about how NVIDIA GPU Cloud is actually used in Taiwan, in the biggest supercomputing center there. And at the very end, we're going to have Chantana and her team conclude this workshop. Okay, so let's start. As I said, so basically this is an overview of the things that we are going to talk. Accelerated computing is the path forward. There are a lot of things that make this happen. There are a lot of things that are needed to make this happen, from the hardware all the way to the software. And there's a lot of things in between. As I said, NVIDIA is working not just to produce the latest and greatest GPUs. So you already have a couple of them. So as Professor Pujong already presented, you do have the hardware in-house here available for you. But there are a lot of other things that need to come together in order for you to get the performance out of the hardware. And we are trying to work on all these fields, and we're going to talk about these different components. Whether we are talking about traditional HPC, which is physics simulation, whether we are talking about using the system for AI in new ways, and again, you're going to understand what I mean by that. Working on the full stack optimization, again, if you look at the agenda that I'm proposing, and This was intentionally done, so I'm not going to talk that much about hardware, but I'm going to focus on the different libraries or different SDKs that we provide to make the life easier for you as a user. And last but not least, developer productivity. It doesn't matter if you're doing HPC, it doesn't matter if you're doing deep learning or AI. We have different tools, and I'm going to try to do an overview of all these, or a vast majority of these tools that you can take benefit when you're using an accelerated system. Again, just to set the context, we're talking about high performance computing, and I've been doing high performance computing for the past 10 years. If you've been in the field of high performance computing traditionally, it was just simulation. So you're applying the laws of physics to a certain simulation, and you're running that at a very big scale. So that was the traditional high performance computing. But now more and more you're actually having new fields, a new HPC market, and because this is including things like deep learning. The type of requirements, the type of operations that are being done when you're doing deep learning are becoming very similar to what you require for a traditional HPC simulation. The same for machine learning. Again, machine learning has been around for many years. People were doing machine learning, but the requirements and the technologies that are being currently used for machine learning, they become once again similar to those of traditional HPC. And to understand why do we need such technologies for all this, what we are calling a new HPC market. If you look at the graph here on the right hand side, basically the blue line shows you the performance of a CPU, of a traditional CPU that you have in your system, you have in your laptops. Traditionally, the CPU was the workhorse for all your computations. So whatever you were trying to compute, it was being done on the CPU. Over the years, the performance of the CPU kept increasing. So as a developer, as a programmer, even as a mere user, you didn't have to do anything. You're basically just waiting for the next CPU to come on the market, and your program would just run faster because the new CPU, it was just faster. And you kept waiting for the next version of the CPU, the next version of the CPU, without thinking too much what's behind all that, behind the technology, what makes that technology possible. But if you look in recent years, this trend is actually starting to plateau. So you don't get that the same performance that you were expecting generation over generation. What we did at NVIDIA around 2007, so again, you probably know NVIDIA for doing very good graphic cards for games. And that's what a lot of people actually know about NVIDIA. But we're doing a lot more than that. And this changed around 2006 when we decided to introduce what we are calling the first fully programmable graphic processing unit. So previously the GPUs were only used to do gaming, render very nice scenes, but we thought why not use the same architecture and make it fully programmable in order to support generic computations. This is actually how the field of GPU emerged. And GPU, for those of you who don't know, is general purpose graphic processing unit. And more recently we call this more generically GPU computing. Even at that point in time, when we first introduced the first programmable architecture, we were already an order of magnitude more performant than a CPU. That doesn't mean to say that any program that was running on a CPU automatically would run on a GPU. We are far from there even at this point in time. But if you are able to put your program, whatever computation you're trying to do, in the format of the GPU, then you get a very big boost in performance. And then year over year, we managed to increase this performance through different means. Obviously, innovations in the underlying architecture. We are introducing new stuff, and I'm going to talk a little bit later about different things that we're introducing in the very latest architecture. Things like tensor core. Again, for those of you who have some experience with GPUs, you might have heard that term. Or if you're doing deep learning, is one of the architectural features that makes the GPUs right now basically the number one or the go-to chip for deep learning. But the architecture is not everything, and having a good architecture is not everything. You also have, as I said, and I keep mentioning this over and over again, you have to have a good software stack. And here, if you look at the right-hand side, so this is only a mock-up of what we are calling the NVIDIA platform. So obviously, at the very bottom, you have the architecture, whether you're talking about the chip or the server that includes the GPUs. And then you have all the other layers, starting with the CUDA programming language that is a very easy entry point into programming GPUs. We're going to talk about that later on. And then you have integration into the systems, algorithms, and application. So we are trying to work across this entire stack to make it easier for the developers, make it easier for the users. And we're actually predicting that by 2025 there will be a gap more than 1000x between the performance that you would get from a traditional CPU and the performance that you get from a standard GPU. So this is just to set the context. If we go a little bit deeper into what we are calling the NVIDIA platform, it looks something like this. As I said, at the very bottom, you have the architecture itself, the hardware. The next layer, which is very important, is the CUDA programming language. The CUDA programming language was introduced once we released that first GPU programmable, the first fully programmable GPU. CUDA language was designed to be an easy way to program GPUs. Previously, it was fairly complicated to even design a game or do operation on the GPU. With the CUDA programming language, anyone who knew a little bit of C or C++ was able to program a GPU. So very low entry point. But obviously, when we first introduced CUDA, there were only a handful of people that knew how to program CUDA, and for the rest of the users, it seemed pretty complicated. So the next step that we did was to build some core libraries that were providing functionalities. These libraries were developed by our own engineers, and these libraries were providing different functionalities. And then we kept extending these libraries over the time. Right now, if you look at this level here, we have more than 50 libraries in all the fields from, again, traditional HPC, so things that are doing operations like FFTs, basic linear algebra, this kind of operations, going into deep learning, so things that are providing primitives for deep neural networks, tensor runtime. Again, I'm going to talk about all these details later on, and then more recently, machine learning. So we have a huge array of libraries that are now under the umbrella of what we are calling CUDA-X. And you've probably seen in my agenda I was mentioning CUDA-X. So CUDA-X is basically an umbrella of all the libraries that are right now available. They're all implemented in CUDA and they're optimized to run on the GPU. The next layer is the application layer. Most of the time, if you are a user right now, you don't even need to care about how to program in CUDA or how the libraries actually work. You just run one of the applications, whether we are talking again about HPC or machine learning, deep learning, or commercial software. There are a lot of commercial softwares right now that support GPUs. And last but not least, it's an entire field of applications. You've seen a couple of examples, again, in Professor Puchong's presentation, mostly on deep learning. But there's an entire array and an entire array of fields where GPU computing can be used to accelerate the work The NVIDIA platform is, without any doubt, the most adopted platform for accelerated HPC, and the numbers tell it, tell everything. So just the number of, for example, in this case, of CUDA downloads. So remember, CUDA is the programming language for the NVIDIA GPUs. In 2014, we had 3 million downloads. This year, actually, I think this is the number from last year till today, 13 million downloads. It's a huge increase in the adoption of the CUDA programming language. Number of accelerated applications. Once again, at the beginning when we first launched the CUDA programming language, obviously we didn't have a lot of applications that out of the box were able to use GPUs. But now, we're in 2019, we have more than 620 applications that are already GPU accelerated. So if you're using an application, let's say you're doing computational chemistry or computational fluid dynamics or deep learning, you don't even need to think about all the details on how to start programming on the GPU. If you're using an application, just look if that application, we actually have a catalog of applications that is always kept up to date. Just look into that catalog, and maybe that application is already GPU accelerated. And you have the hardware here. Just request your system admins to install that application and make it available for you, and you can already benefit from the acceleration. And last but not least, there are a lot of systems in the world that are using GPUs, and I'm going to talk a little bit later about that. Obviously, it's also the most adapted platform for AI and deep learning. There's an explosion of requirements for deep learning capabilities. The GPUs have always done a tremendous job in accelerating the deep learning computations, whether we are talking about the training part, whether we are talking about the inferencing part. And again, I'm going to go into a lot more details later on. But let's take each of the field that I mentioned. So remember, I was talking about the new HPC market. We're still talking about the traditional HPC in the traditional way, where you have big supercomputer centers where you're running one single application that is actually trying to scale across multiple nodes. And this is a list, again, just to show the level of adoption. The #1 biggest supercomputer in the world, this is in the US, Oak Ridge National Lab, 27,000 GPUs in one single system. Second largest system, again, in the world, also in the US, more than 17,000 GPUs. We also have the biggest supercomputer in Europe. We have the biggest supercomputer in Japan. Right now, if you're Googling today, we just released yesterday the announcement for the biggest supercomputer in this part of the world in Australia. NCI in Australia, they just announced to purchase more than 600 GPU system. And also this one here, and I skipped it on purpose, most of the time people think that HPC is only for academia and for researchers, professors that do some very fancy stuff. This shows that is not true. A lot of industry are starting to use high performance computing, and we have, again, the fastest industrial supercomputing. This is Total company, so an oil and gas company in France. They have a 18 petaflops, so more than 3,000 GPUs used for oil and gas. So again, if you look at the whole evolution over time of the top 500, again, if you've been doing HPC, you've probably heard about the top 500. It's basically the ranking of the most powerful supercomputers in the world. More than 125 systems in the top 500 actually have accelerators. So just to put it in perspective, that accelerated computing and GPU computing, it's not something esoteric or something that people are just starting to discover. It became mainstream. And why do you need so much computational power? These are a couple of examples that require massive computational power. So whether you're talking about chemistry, trying to discover the next generation of lithium-ion batteries, 3 million node hours are required to do this kind of simulations. Climate modeling, again, it's a very important problem no matter where you are in the world. And having an accurate weather prediction, it's not just for, let's say, for the mere user that you need to know, you want to check your phone and you need to know how the weather is tomorrow. There are a lot of industrial applications that are basically they're critically depending on weather simulation. So things like running an airport, so aviation, transportation, they all depend on a very good and accurate weather prediction. 100 million hours are required to do an accurate simulation. Medicine, healthcare, where we start talking about precision medicine, where your genome is actually identified and you get a very accurate diagnostic of your condition and you get a very personalized treatment. Again, 10 million node hours required to do this kind of simulation. So there are a lot of applications that require a lot of computational power in a very broad spectrum of fields. Once again, industry. All this, again, it might look, if you look at the different applications, at this point in time, most of them are in the realm of research. But there's a lot of industries that are actively employing HPC for all sorts of things. And again, these are just 3 examples. The first one, it's more or less obvious, I already mentioned it, Total is doing that. This is another example with another partner. We were working on petrol discovery. This one, real-time fleet analytics. Again, it's a very important problem when you have a fleet of vehicles that you have to deploy. This is a partnership with the United States Postal Service, where you have to, where they have thousands and thousands of vehicles, and they need to optimize the route for deliveries. And this is an HPC problem. Engineering, all the cars, all the vehicles that are designed right now, whether it's cars, trucks, airplanes, they're all being simulated right now in in a virtual environment. So all this computational fluid dynamics require a lot of computational power. And the pinnacle of research, you probably heard about this, it's called the Gordon Bell Prize Award. These are the highest achievements in the HPC research. And again, I'm not going to go specifically into the details. You can either look for it or I can provide you the references. But 5 of the 6 finalists, they required GPU computing in order to be able to run the simulations that they've been doing. And they're all very interesting, they're all very innovative in their own way. And I'm not, as I said, I'm not going to go into the details, but just take a look once again at the numbers. Oak Ridge National Lab, so the biggest supercomputer. There's also research on opioids addiction in the US. They required 2.36 exaflops in order to run their simulation. So we're already talking about exascale. So exascale becomes the holy grail right now in HPC. Obviously, we're going to get there sooner rather than later, but the requirement is already there. As I said, those are the pinnacle of the HPC research. But no matter what type of work you're doing in a more traditional way, we have more than 600 applications. Again, I don't want to go into all the details and talk about each and every application, but here I just want to show you that right now it doesn't really matter which field you're working in. I'm pretty sure that at least one of the applications that you're using currently to do your computations is already GPU accelerated. And unfortunately, there's a problem with the screen here, but I put here at the bottom a link where you can actually access this application catalog, and you can download the, if you just search for NVIDIA GPU application catalog, you're going to find this list of all the 600 applications, and we keep updating this list almost every week. And again, just to give you an example, I chose this application because, again, Professor Puchong told me that there might be some users around here. This is Amber application, and this shows the performance, and this kind of charts you're going to find in that application catalog for almost each application. If you look at the performance that you get for Amber, it's a standard molecular dynamics application. In order to get the same performance that you would get from one single server with only 2 GPUs, you would need 48 CPU servers instead to achieve the exact same performance. One server with 8 GPUs, the one that you just got, the DGX1, it has 8 GPUs right now. The same thing that you can run on that one single server using all the 8 GPUs, you would need 202 CPU servers to achieve the exact same performance. So huge benefits in performance when you're using an application that is already GPU accelerated. I'm going to check the time. And maybe this might not concern all of you, but again, it's good to know. It's not only that you get an increase in performance and you get as you've seen, for example, instead of using 200 servers, you just use one accelerated GPU server and you get the exact same throughput. But from a data center perspective, you also get a lot of benefits. You get benefits in terms of cost, because obviously one GPU server, it's not as expensive as 200 CPU only servers. You're saving in energy cost, because again, the energy to power one single GPU server, it's way smaller than powering 200 CPU servers. So a lot of savings in cost, power, and space in the data center. This is more on the infrastructure guy perspective, but again, it's good to know that when you're switching to a GPU accelerated platform, you do get to do a lot of savings. But as I said, I'm not going to talk about the infrastructure today because it's not the purpose of today's talk. I'm going to focus more on the software side. And as I said, the CUDA platform and the CUDA programming language is actually the foundation of the entire NVIDIA ecosystem. And the CUDA programming language, depending where you want to have your entry point, you have multiple choices. You can, depending on the ease of use, or if you want specialized performance. So I'm going to start from this side, which is the low-hanging fruit and the easier entry point. And I already mentioned this, and I'm going to skip this part. It's basically just take an application that is GPU accelerated, use it on a GPU system, and go with it. The next easier part is using frameworks. Frameworks, especially in the deep learning space, you're going to hear a lot about deep learning frameworks. Things like TensorFlow, Caffe, Tiano. All the major deep learning frameworks right now are GPU accelerated. Underneath the framework, they are using the NVIDIA